Hey, Denell High School AP Physics. This is the last installment of Fluid Mechanics. This is 6.3 Bernoulli's Principle, and if you've ever wondered how to fly, I believe I can fly. You want to know Bernoulli's Principle because this is how we fly. So let's get going. First, we want to talk about the volume rate of flow. You see that word volume? It means volume. You see that word rate. What does rate always mean? Is per seconds, right? The volume rate of flow. And so the equation for the volume rate of flow is the amount of volume per second, right? The amount of volume divided by the time in seconds. Or we can say it's area times velocity. Area times velocity. And why is it area times velocity? Because area times meters per second, okay, gives you volume divided by seconds. And of course, for area, we can use the pi r squared if we're talking about a faucet, like the little picture on the right, pi r squared times my velocity, because that would be my area. And so my units for volume rate of flow would be in meters cubed, because that's units for volume, divided by seconds, of course. Okay? So that's volume rate of flow. Now, we have this thing called the continuity equation, and what the continuity equation is whenever we have like pipes that change sizes, okay, from one size, from one area or one radius to another area or another radius, the velocity of the fluid changes as well. You can see these lines in this picture right here. The lines get closer together, so the velocity actually increases. Okay, the smaller the radius, the faster the velocity. Just try this on your little brother or little sister. Just say, "Man, I gotta take a look at some physics." Take them out to the hose outside and have the water just flowing out of the hose, and then put your finger over and change that radius of that hose and spray your little brother or sister. It's pretty fun. Okay, and so here we can use the volume rate of flow at one point is equal to the volume rate of flow at the other point. It's conserved. Okay, and so something you'll see is Bernoulli's equation. It's all about conservation here. It's all about conservation. And so that means the area times the velocity, A1V1 equals A2V2. Anytime you have pipes changing, guys, use A1V1 equals A2V2. And you could also use pi r squared V1 equals pi r squared V2. Okay, one scenario and another scenario. Again, it's just conservation. It's very much like conservation of momentum, isn't it? Okay. Of course, the pies can cancel out, and you'll be getting some pie pretty soon for Thanksgiving. You take a look at this picture right here. You can see what happens to the pressure when we have a faster speed is the pressure gets lowered. This is what happens in a hurricane. When the speed gets faster and faster, actually the atmospheric pressure gets lower and lower because the particles are being pushed out faster and faster. Okay, so greater the fluid flow speed, the lower the pressure. Okay, and then it finally brings us to Bernoulli's equation. Bernoulli's equation. You can see here is all of our equations. You can see the top equation is our equation for Pascal's principle. Then we have Archimedes' principle with the buoyancy, and then you can see we have the continuity equation, and then the last equation is Bernoulli's equation. Now it says P plus rho gy plus 1/2 rho v squared equals constant. When you see this equation, when you see Bernoulli's equation, I want you to take this equation and make it become this. Instead of using the y, use height. Okay? And instead of saying it equals constant, make it equal to each other. Now I hope you see this looks very similar to mgh plus 1/2 mv squared. Okay? It's ultimately energy with fluids. It's energy with fluids. So let me show you how to use this in a problem. Here we have a fountain. It has an opening of radius 0.01 meters. It shoots water directly vertically at 5 meters per second, and the first thing we want to find is our volume rate of flow. Okay, and so my volume rate of flow is of course my area times my velocity. My area of course is pi r squared. I have a circle times velocity, so I have pi, my radius 0.010 squared, and my velocity is of course 5 meters per second, and I end up getting for my volume rate of flow, ends up being 0.00157, and of course volume is meters cubed, rate is per seconds. And so that is the answer to A, my volume rate of flow. Now when we end up getting to B, we're going to take a look at the absolute pressure in the point. Okay, anytime you end up doing Bernoulli's here, and I'm going to erase this real quick and come back, anytime you end up doing Bernoulli's, I like to draw my picture right here. Okay, if you label everything, guys, Bernoulli's problems become so easy. So in class, on test, label everything. Here at this point right here, I'm at a height of 0, aren't I? I'm at the lowest point, so I'm going to call that 0. That's my frame of reference. It has a radius of 0.020 meters. That's what it said in the problem. It's fed by this change in the radius there. And I don't know what my velocity is. It's a big question mark. They didn't tell me. Now up here, at this point right here, which I'm going to call this point down here point A, and up here I'm going to call this point B. Okay, this is actually at a height of 2 meters, isn't it? Because the last one was 2 meters below, and so I'm going to call this 2 meters above there, okay, above 0. My velocity was of course 5 meters per second, and my radius was of course 0.1010 meters, okay? And you can see I need to find my velocity first, okay? So what am I going to do is use the continuity equation. A1v1 equals A2v2, and I'm going to call this side A, and I'm going to call this side B. And so I'm going to use pi r squared. This is at point A, which is 0.020 squared, and my velocity is, I don't know, that's what I'm trying to find. And I have pi, my radius is 0.010 squared, and my velocity is 5 meters per second, and I'm going to find my velocity. And so my velocity at point A, below the ground, ends up being 1.25 meters per second. Okay? When you do this, guys, you can cancel out the pi's there. And so right now, I'm going to come down here, I'm going to write in 1.25 meters per second, because that is what I know is my velocity at this point down here. Okay? Now, I'm going to just erase this. You can always rewind and come back to that. Okay? And now I'm going to go and do Bernoulli's principle. Now, Bernoulli's principle is pressure plus rho GH plus 1/2 rho V squared equals pressure plus rho GH plus 1/2 rho V squared. Okay? And so here we go. This is going to be side A over here. This is going to be side B over here. Okay? So now, because I labeled everything, I know where everything goes. I'm trying to find the pressure at A. That's what I'm trying to find. So I'm just going to put P. I know my density of water is 1,000. I know my gravity is 9.8. And this is at a height of 0. Okay? So that cancels everything out there, which is nice. Okay? Here I have 1/2. I have 1,000. And I know my velocity now. It's 1.25 squared. Okay? And when I calculate all of that, I get 781.25. Okay? Now, guys, this is the big point. Do you see how it said, I want to find absolute pressure? If I want to find absolute pressure, for this pressure right here, I want to put in 1 times 10 to the 5th. Okay? If I wanted to find gauge pressure, and I'll say this again, if I wanted to find gauge pressure, you do not need that pressure. That is 0 if it's gauge pressure. Again, this number right here would be 0 if I was using gauge pressure. Now I'm going to do rho GH. I have 1,000. Okay, and so 1,000 times gravity is 9.8. My height is 2. Okay, and let me fill in some numbers here. I have 1 times 10 to the 5th. If I do that calculation right there, I get 19600 plus, and I have 1/2 mv squared. 1/2, sorry, not mv squared. 1,000 v squared is 5 squared. Okay, and when I end up getting that, I end up getting 12500. Okay, now if you see, I'm going to add up all of these numbers, and I'm going to subtract the 781.25, and I end up finding the pressure absolute to be 131318.75 pascals. Now, of course, if I wanted to find gauge pressure, I would just subtract 1 times 10 to the 5th. I don't need that pressure, that absolute pressure there. Okay? But this is how you do Bernoulli's problems. How do you do Bernoulli's problems? Do A1v1 equals A2v2. Find all your velocities. Find all your radiuses. Find all your heights. Okay? Label everything. And then all you have to do is plug it in. Bernoulli's equations. Guys, I hope this helped. I will see you in class. Take it easy. Bye.
Bernoulli's theorem and its applications. Daniel Bernoulli, a Swiss mathematician and physicist, stated a theorem which gives the interaction between the pressure acting at a point on the surface of the liquid and the velocity of its particles. Bernoulli's theorem states that the total energy of a small amount of an incompressible liquid flowing from one point to another remains constant throughout the displacement. The illustration shown here will help you understand Bernoulli's theorem. Motion of a ping-pong ball. Place a ping-pong ball in an upward stream of water as shown here. We observe that when a continuous stream of water gushes out of the nozzle, the ball rises to a certain height above the nozzle and stays at that height against the gravitational pull and starts spinning. We also observe that in case the ball moves to one side, it is automatically brought back to the original position. How does this happen? Suppose the ball moves towards the left. The ball continues to spin due to the liquid on the right side. The direction of spin of the ball is in such a way that the fluid velocity is more on its right side and less on the left side of the ball. According to Bernoulli's theorem, the pressure of the fluid on the right is less than that on the left. Due to this difference in pressure, the ball returns to its original position. Rise of oil in a narrow tube. Shown here is a horizontal tube AB dipped in oil. The area of cross-section of the tube at C is much smaller than that at A and B. Observe the movement of water when it is flowing from A to B. At the narrow end C, the velocity of the water increases and hence the pressure at that point decreases below the atmospheric pressure. Due to the difference in pressure, the oil rises into the vertical tube. Applications of Bernoulli's theorem. The principle underlying the working of atomizer, Bunsen burner, flow meter, and aerofoil is Bernoulli's principle. Atomizer is an instrument used for spraying perfumes and water. The experiment shown here gives the principle underlying the working of an atomizer. Displayed here is the arrangement used in an atomizer. When the rubber bulb B is squeezed, the air flows through the tube T and comes out of the narrow aperture O of the tube. As the aperture is narrow, the velocity of the air increases as it comes out. This reduces the pressure in the vicinity of O. Due to the difference in pressure, the liquid rises up into the vertical tube. But the stream of air coming out of the tube T blows the liquid into a fine spray. So next time you use perfume or deodorant, remember this principle. Bunsen burner. One of the most commonly used appliances based on Bernoulli's theorem is the Bunsen burner. In a Bunsen burner, when the gas emerges out of the nozzle, the velocity of the gas increases and as a result, a region of low pressure is created around the nozzle. As a result, the atmospheric air flows towards the burner and the air necessary for combustion is sucked through the holes present on the burner. Working of flow meter and aerofoil are also based on Bernoulli's theorem.
First, let's begin with a description of the equipment. On top of the workbench, we have the Venturi apparatus. The Venturi apparatus is comprised of a Venturi section connected to 11 piezometers. From left to right, the piezometers are labeled A to L, skipping the letter I. Next to each piezometer is a graduated scale. The valve on the right-hand side is used to regulate flow through the Venturi apparatus. Next is the weight measuring tank, which is located below the workbench. This tank is used to trap water flowing through the Venturi apparatus. The lever arm at the front of the tank is connected to weights. There's a handle at the front of the weight measuring tank. This handle is connected to a mechanism which acts as a plug to the tank. Below the tank is a water reservoir which is used to supply water to the Venturi apparatus. Now we will check that the apparatus is set up properly. First, make sure that the red valve is completely closed by turning it clockwise. Ensure that the piezometer levels are reasonably equal and high enough, but not off the reading scale. If so, please alert the teaching assistant. Now make sure that there's no air trapped in the piezometers. If so, gently tap them in order to remove the air bubbles to the top. Ensure that a weight of 9 kilograms is attached to the free end of the lever arm. This should comprise of the 7 kilogram silver weight and hook and an additional 2 kilogram free weight. Make sure that the weight measuring tank is unplugged by keeping the lever on the front of the tank in the horizontal position. Going into the procedures of this experiment. First, set the flow at maximum capacity by opening the regulating valve slowly. This is obtained when the lowest piezometer reading is about 1 centimeter. This should correspond to the reading of the piezometer at station D. Throughout the experiment, make sure that the water level in any piezometer never goes lower than 0 on the scale. Every time the flow is adjusted, wait for a few seconds in order for it to stabilize. Take note of this reading at station D. Next, we will set the flow to a minimum. Reduce the flow by closing the valve slowly, such that the difference between the highest reading at piezometer A and the lowest reading at piezometer D is about 2 centimeters. Now take note of the reading at station D for the minimum flow. Next, we will determine the intermediate flows. First, determine the difference between the two extreme readings for piezometer D. Then divide this difference by 3 in order to roughly determine the interval between the two intermediate piezometer readings at station D between the maximum and minimum flows. Record the piezometric head in all piezometers for this minimum flow from left to right. Next will be a description of the discharge measurement. Make sure you have a timer at hand. Look into the weighing tank and try to understand the mechanism of the stopper. By turning the lever on the front of the tank counterclockwise in the vertical position shown, the drain at the bottom of the tank will be plugged. Similarly, when the lever is turned clockwise in the horizontal position shown, the drain at the bottom of the tank will be unplugged. This is an actual demonstration on how to measure discharge. Now turn the lever counterclockwise in the vertical position and start the timer. After doing so, ensure there is no water leaking from the bottom of the tank. Turn off the timer as soon as the balance tips over. The time recorded is the time required to accumulate 9 kilograms of water. Remember to unplug the tank by turning the lever clockwise in the horizontal position so that no water accumulates in the tank before starting any more runs. Now adjust the flow to a higher discharge. Then record the piezometer readings and measure the discharge as previously described. Repeat the step for the remaining flow adjustments. After the last flow adjustment, turn off the flow completely by turning the red valve clockwise. This concludes the procedures for this experiment. The following procedures is for the startup of the apparatus. Make sure that the pump is turned off. If needed, add water in the bottom reservoir using a water hose such that 3/4 of the reservoir is filled with water. Ensure that the power cord is plugged into the wall. Make sure the valve of the apparatus is turned off by turning the red valve clockwise. Start the pump. Remove any air bubbles from the manometers by tapping gently on the manometer tubes. Make sure that all the manometer readings are high and approximately equal. If not, seek help from the lab technician. Check that the Venturi device is operational by increasing the flow and observe the pressure drop in the manometers. The pressure drop should look like the following. The following procedures is to shut down the apparatus. Now turn off the flow completely by turning the red valve clockwise. Now shut down the pump and unplug the power cord from the wall and stow it in a safe place.